So we start once again the spectral fatigue analysis with some new challenge. So this is a group discussion kind of thing. Today's task is different. We are going to link waves we see here to the stress cycles that cause fatigue in this beam. Okay. So what we are going to do is that we are going to link the waves we see and stress cycle that's going to cause. So we start from the waves and somehow end up with the stress inside the metal. So you'll start with waves and then we will end up with the stress, right? So that's where RAO, the response operator, amplitude operator comes in. So response operator is nothing but it's linking the stress inside the beam and then waves what we see in the ocean. Okay, so understanding RAO concept. RAO sounds fancy. What does it really mean? Think of RAO as a translator between waves and structure. Mathematically, RAO tells us how much the structure responds. RAO means like how much the structure responds. It tells us how much structure responds in motion, force, or stress for a given wave amplitude at each frequency. So we are giving one wave amplitude at each frequency, different frequencies. Okay, and then how once we apply that one, how the structure is going to respond. That is the information given by RAO. So we could say that RAO is the ratio of response amplitude at frequency f and then wave amplitude at frequency f. So if a wave height of 1 meter hits, the beam bends by 0.1 meter, then RAO is 0.1. Say example, this is my tubular beam, and then wave height 1 meter, this is my wave height 1 meter. It's going to hit the structure. So structure, what happens? It's deflecting like this. So deflection, you can see it bends. Say deflection, you see this is a 0.1 meters and wave height 1 meter. So RAO is the ratio of this response 0.1 divided by 1 at that particular frequency. So its RAO becomes 0.1. So exactly that means the structure responds 10% of wave heights at that frequency. So but RAO can vary with frequency, right? It varies with frequency. Yeah, the beam may react strongly to some wave frequencies. Suppose this wave frequency is say 1 by 3 second, and structure also 1 by 3 second, means it could deflect further more, right? It could respond strongly, and sometimes it weakly responds to others. The RAO curve shows the frequency dependent sensitivity. The RAO curve shows us this in the frequency dependent sensitivity. Suppose if you have different frequency, and some frequency it is 0.1 only, it's displacing, and some frequency it goes to 0.2, 0.3, something like that. So we can see that some particular frequency in the structure responds quite strongly. That's nothing but that is the resonant condition. So RAO gives us the frequency dependent responses. So the responses in this y-axis and frequency in the x-axis. Connecting RAO to the stress. How are we going to connect the RAO and stress? Once we know how much structure moves, we can compute the stress caused by the motion. Once we know the displacement, we can cause the bending stress, all these things, right? So if the motion, displacement, or acceleration is proportional to the stress, we can write sigma is the sigma RAO times SNF. SNF is the wave spectrum, energy in the waves at each frequency. RAO we know, so this is the response, right? And so the RAO acts like a filter, shaping which wave frequencies actually cause stress, which wave frequencies actually cause perfect analogy. It's like a tuning guitar string, only certain notes make it vibrate strongly. That means if the sea has many frequencies, the beam only feels the ones that matches natural frequencies or where RAO is high. So exactly that's how we connect the sea's randomness to material stress. The stress per spectral density, we can say it. Once we multiply the wave spectrum by square of the RAO, we get the stress spectrum. This is the stress spectrum. Once we multiply the wave spectrum by square of the RAO, so we can get this is the PST of stress. So sigma tells us how much stress energy comes from each wave frequency. Now the stress spectrum is our starting point to find fatigue damage, but we need to describe how random the stresses are. So let us think about the spectral moments again. We calculate the spectral moments using this formula. So m0 is like a total energy of the stress. m2 tells us how fast it changes. So from them we find the root RMS value and the t set average zero crossing period. These two we need, RMS value and zero crossing period. These tells us how strong and how frequent the stress cycles. This is how strong the stress cycles and how frequent the stress cycles. m0, higher m0 means stronger the stress, higher m2 means faster it changes. And this is actually square root of m0 by m2 t set. So So yes, that's crucial for fatigue because both strength as well as frequency of stress, strength of stress as well as frequency of stress, both matter. Now we will distribute the entire radial distribution. Now we have to distribute how stress amplitudes are very distributed. So for example, this is the stress amplitudes and this probability. So we have to see how the stress amplitudes are distributed. The stress is not constant, sometimes big, sometimes small. That's where the Rayleigh distribution comes in. When the stress signal is random and Gaussian, the amplitude of stress range follow this is the stress range. Okay, the amplitude of stress range follow Rayleigh distribution when the signal is random and Gaussian. So this is the probability of that distribution, right? So what does this mean in simple terms? It means small stress ranges are very common. These are the small stress ranges. Small stress ranges are very common, and big stress ranges are rare. Big stress like small waves are frequent, and some storms are rare. Exactly. This equation gives us the probability of each range. So for each range, what is the probability? For each, so some particular stress range, the probability is quite high. Some, if the stress ranges are very high, bigger stress events, the probability is very less. Small stress events, that probability is somewhat moderate. This particular some region of stress ranges, the probability is quite high. So sigma naught is RMS stress. So if it's larger, we will get more stress cycles. Increasing sigma naught spreads the distribution out and more chance of damaging the larger from probability to number of cycles. From once we get the probability, then we will get the number of cycles. Now to find how many cycles of each stress range happen, we need to find out how many cycles of this stress range. This is the stress range. This is how many cycles of that particular stress range is happening. We multiply the probability. This is the probability with total number of cycles. N is the total number of cycles. Pi is the probability of that stress range. So we can get that stress range, how many cycles is going to happen, how many cycles of each stress range happen. So if N is 10,000 cycles per hour, sigma naught for that particular probability for that 20 MPa stress range is 0.02, then 20 MPa, how many times it's going to happen? So that means like 0.02 into 10,000, that means 200 cycles is happen with the stress range of 20 MPa. So with the different stress ranges, we can get the number of cycles, how many cycles for each stress range is going to happen. So now comes the material part. How many cycles can material survive at each stress range? Some particular stress range, how many cycles the material can survive? That we can get it from the SN curve. That comes from the SN curve. SN curve equal to N equal to A by sigma range, stress range power M. A and M are material constants. Material test. From the material test, we can find out A and M. So high stress means fewer cycles to failure. Double the stress, life can drop by 1/16 if M equal to 4. 1/16. If double the stress, life can drop. So stress plays a lot. Even small stress changes also, it becomes 1/16. So then we calculate the damages per stress range. Number of cycles we can put it. Actually, for that particular stress range, what is the damage? Integrating all those small damages gives the total damage. So gamma function, this integral looks scary. How does we solve it? This type of integral appears often. This is a common has a known answer using gamma function. Total fatigue damage, we can get it. So what's gamma thing? It's like a continuous version of factorials. It helps us compute these costs that grow quickly. It just helps us sum up all the possible stress ranges weighted by how probable they are under Rayleigh's law. So example calculation. For example, we get the stress of RMS value of 20 MPa, number of cycles is 14,000 per hour, A and M. So we can calculate the damage. So that means like 1.84% of total life is used in 1 hour. In 1 hour, 1.84%. That means how many hours it can go? 1 divided by 0.018. Then it can go quite a lot. So physical understanding. So waves have energy across frequencies. RAO shows how the structure converts each wave frequency into stress response. So how each wave frequency is converted into stress response. And the stress spectrum tells us how the structure vibrates. From spectral moments we get the RMS values and number of cycles. Using Rayleigh we know how stresses are distributed in size. And finally, SN curves we find the total fatigue damage. That's the power of RAF Rayleigh method. It connects the environment and microscopic life of the materials. So if we change the RAO, make the structure stiffer, the stresses go down. RAO would become smaller, reducing stress spectrum, hence smaller M naught, smaller RMS, and less fatigue. If you have a rougher C, bigger wave spectrum, stress, PSD, and damage both go up. The environment and design together decide the fatigue life. RAO connects external forces, Rayleigh connects internal randomness. RAO translates the C squares into predictable structures, so Rayleigh translates that the stress probabilities, and we can use it for damage prediction.